All right, our next speaker is Qianyu Hou, who will talk to us about early detection of ASD before age 2 via cortical morphology and explainable geometric deep learning.
Well, good days, everyone. Actually, I'm not the author, but on behalf of all the authors, I'm here to present this work. This work is about the early detection of ASD before age 2 via cortical morphology and explainable geometric deep learning, and this work tries to address a critical gap in early ASD diagnosis with interpretable AI. And I have no disclosures. And ASD is a neurodevelopmental disorder. Brain imaging shows that structural differences between ASD and the typical development infants actually within the first 2 years of life. However, current diagnosis relies on behavior science after age 3, missing a critical intervention window. To analyze early brain development, one option is to leverage neuroimaging to reconstruct the cortex as a detailed 3D mesh and to compute cortical attributes. Then we could carry out surface-based analysis, which can localize neurodevelopmental morphological abnormalities precisely. While explainable deep learning has been explored actively, applying these methods to neuroimage data faces 2 key challenges. First, most approaches are designed for gridded data like 2D images. For 3D brain meshes, advanced techniques such as cervical U-Net map meshes to cervical surfaces, achieving good accuracy, but these models lack interpretabilities. Second, existing explainable methods rely on post-hoc, which are first trained for a specific task and then analyze the underlying correlations offline. But these interpretations are shaky. They depend heavily on training data and often don't reflect how the model actually decides. Unlike post-hoc methods, we argue that explainability should drive classification, but not explain it. So we design an end-to-end framework where we learn fine-grained explanation factors directly. As the figure shows, the method is named NeuroExplainer, and the NeuroExplainer takes cortical attributes as inputs and uses a hierarchical attention decoding architecture, which with 2 parts, an encoding branch and an attention blocks. The encoding branch creates task-related attention on dense-sampled brain surfaces. It has 4 cervical convolution blocks. Each use 1 ring hexagonal convolution plus batch norm and ReLU to pull out vertex-level features. We downsample with hexagonal map pooling except the last layer to feed the next stage. The decoding branch gives fairly coarse explanation factors. To fix this, we design a learnable cervical attention mechanism for weakly supervised precise localization. First, take left hemisphere and right hemisphere as vertex-level inputs. We use global average pooling to get the holistic feature vector. Then a shared 1D convolution map to get attention. And hemisphere attention comes from the weighting. We also use the skip connections and transposed convolution to push these coarse attention to higher resolution brain surfaces. Finally, combining fine-grained attention from low and high resolution, we use GAP again and the 1D convolution to get the classification results. To enhance the discriminative feature learning, we introduced the task-oriented regularization guided by infants' brain development insights. Our approach enforces 2 key properties in attention maps. First is the sparsity for ASD cases. Since ASD-related cortical changes are localized, we use an entropy-based regularization to make attention maps focus on the specific abnormal regions. And the second is the fidelity for normal regions. The non-abnormal parts of an ASD brain should still behave like healthy tissue. Thus, we designed a contrastive penalty to ensure the model learns normal development patterns alongside the abnormalities. The basic idea of contrastive learning is that to pull the similar parts like they are to a closer space and to push the different parts away. We tested the NeuroExplainer on the IBIS dataset, a major longitudinal study of ASD infants. It includes 76 ASD versus 278 TD infants with 829 MRI scans taken at 6, 12, and 24 months. For each scan, we used 3 core metrics: cortical thickness, surface area, and volume. Table highlights the competitive performance of the NeuroExplainer across multiple matrices. NeuroExplainer outperformed in all matrices, especially in sensitivity, which is crucial for clinical applications. Despite class imbalance, NeuroExplainer achieves the highest in sensitivity and distinguishes features associated with autism. Moreover, our NeuroExplainer has revealed the spatiotemporal heterogenesis, neurodevelopmental abnormalities in autism children of different age. At 6 months old, the brain regions of primary focus are mainly related to the motor area and visual area. By 12 months, it gradually affects the memory system, and at 24th month, the developmental abnormalities have involved brain regions related to social-emotional functions. These findings confirm that the interpretability of NeuroExplainer is not only fine-grained, but also aligned with the development. So thank you for your attention, and if you have any questions, I may not take any question, but if you have any question, you can contact the author, Wang Fan, with this email. Yeah. Thank you very much.